Today we're going to talk about Hess's law and standard enthalpies of formation, and we're going to talk about how to use Hess's law and these standard enthalpies of formation to determine enthalpy of reactions that we're going to study in this topic today. So I'm referencing sections 6.3 and 6.4 in your textbook. It's pages 242 to 252. I would have the textbook handy. I also would recommend using the textbook to maybe add to your notes if you feel necessary. The reason I say you need your textbook today as well is because you will have to reference Appendix 4 in the back of the textbook, because that's where the tables of standard enthalpies are, and we are going to be using those for some of the problems that we do today. So enthalpy is a state function. We didn't really talk too much about state functions, but what this means is that it doesn't matter what steps you take to get from reactants to the formation of products, the enthalpy of that reaction will not change. So that means the end result will always be the same. So we could look at this in terms of, let's say we're climbing a mountain. Maybe some people, when they climb that mountain, are going to climb straight up the side to get to the peak of the mountain. Maybe your friend says, that's too much, I'm not going to climb straight up the mountain. I'm going to take this windy path around the mountain to get to the top. What a state function is exactly that. The end result was the same in climbing that mountain. Both you and your friend both got to the mountain. You just got there different ways. So that's what that means. Doesn't matter what steps were taken, the end result was the same. So that's what state function means. Now, if you're taking notes, I would definitely want you to pause the video here to write down these notes, because the best way to understand Hess's law is by actually just doing the problems and explaining as we go. So I do want to say, though, in the first bullet point, not that I like to read things to you, but the enthalpy change for a reaction is the sum of the enthalpy changes for a series of reactions that make up the overall reaction. Now, if you remember, when we did reaction mechanisms, we looked at those series of reactions to come up with an overall reaction. And this is very similar to what we talked about there. But now we're going to put some math to it and talk about it in terms of what is the enthalpy change to get from reactants to products. Now, there are some hints to use Hess's law. I'm going to talk about those hints as we do the problems. So you can pause the video now and you can write down those hints so they have them in your notes. And then we're going to move on to do a practice problem on the next slide. Okay, so here we have 4 different reactions. Each reaction has an enthalpy change with it. What we need to do is look at the overall reaction and try to rearrange or use these reactions to come up with an overall reaction. And then we take all of those final delta H's that we calculate, add them together, and we get an overall enthalpy change for the reaction. So you can see what I want to end up with in this reaction is I want to end up with P4O10 on the reactant side. I want to end up with 6PCl5 on the reactant side, and I want to make sure that I have on the product side 10Cl3PO. So I'm looking at these reactions to see how I can rearrange them possibly to get things on the reactant side and on the product side. So let's take a look at what we have. I notice that the Cl3PO, that is a product, is also a product in this reaction, the 4th reaction. But there's only one of them in that product. So what I need to do is multiply that whole entire reaction by 10, because notice that I have a 10 as a product there. So I'm going to multiply the reaction by 10, so all the coefficients by 10, and then I'm going to multiply the delta H by 10 as well. So let's do that. So I'm looking at the, I'm going to try to organize this as best I can since I'm not on a whiteboard at school. So I'm looking at the fourth reaction and I'm going to multiply by 10. Okay, so I'm going to take that through. That gives me 10 PCl3. Now it's 1/2 O2 times 10, so that means 5 O2. And that yields 10 Cl3 PO. I need to multiply the delta H by 10. So the delta H for this reaction now is a negative 2857 kilojoules. Okay, so that's the first thing that I notice. Now, the next thing that maybe we notice is that none of the reactions have P4O10 as a reactant. I see P4O10 right here as a product. I need only one of them, so the only thing that I really need to do with this reaction is just reverse it. So I need to put the P4O10 as a reactant. So that's the second reaction. So the second reaction I'm going to reverse because I want to get that P4O10 as a reactant. So P4O10 yields P4 plus 5O2. Now, if I reverse the reaction, I have to change the sign of delta H. So if I change the sign of delta H, it's negative 2967.3. Now it's going to be a positive 2967.3. And again, kilojoules working with here. Okay, so that's the second thing. So now I've got P4O10 on the reactant side. I also need PCl5 as a reactant. I don't see it anywhere as a reactant, but I do see it as a product. Let me erase some of this stuff here. Whoops, so that we can see. I do have PCl5 right here as a product, so I could reverse that reaction as well. But if you notice, down here, I need 6 of them. So not only do I need to reverse, I also need to multiply by 6. That is the third reaction. So third, I'm going to reverse, and I'm going to multiply by 6. So if I reverse and multiply by 6, I end up with 6 PCl5 yields 6 PCl3 plus 6Cl2, and I'm going to need to change the sign and multiply by 6 for my delta H. So whatever I do to the reaction, I need to do to delta H. My delta H is negative 84.2 kilojoules. If I reverse it, that becomes positive. If I multiply by 6, I get a positive 505.2 kilojoules. Okay. So now I have both of my reactants on the reactant side and I have my product on the product side. I didn't do anything to equation 1, and I actually don't need to do anything to equation 1. I do need to rewrite it though. I'm not going to manipulate it at all, but I need it because it allows me to cancel items that aren't in the final reaction. And I'm going to show you what I mean by that in a second. So the first reaction, I do nothing. Okay, so do nothing. I think we're all doing a lot of nothing once we get done with our schoolwork, right? Sitting at home. So I'm just going to rewrite this. P4 plus 6Cl2 yields 4 PCl3, and the delta H for that doesn't change because I did not change this reaction at all, so it's going to stay negative 1225.6 kilojoules. Now, we're going to see if we can cancel things from the product side to the reactant side. So I need the 10 PL. The 10 Cl3PO, I'm sorry. I need that on the product side. So I know I want that to remain, and I know I want P4O10 to remain, and I know that I want 6PCl5 to remain. But everything else hopefully will cancel out. If I have it on the reactant side and I have it on the product side, I should be able to cancel. So I notice first that I have 5 O2s here, so I can cancel them with these 5 O2s. This is on the reactant side, this is on the product side. I have 10 PCl3s right here. Let me just switch colors. 10 PCl3s right here. I have 6 here on the product side, and I have 4 here on the product side. So 6 plus 4 is 10. This is on the 10 up here are on the reactant side. These are on the product side. I can get rid of those. So those are gone. Now, I have P4 right here on the product side, and I also have it here on the reactant side. And again, you'll notice that was the first reaction I didn't do anything to, but I need it to cancel some things out. I also have 6Cl2 here on the product side and 6 here on the reactant side, and so those will cancel. So now I have everything canceled, and I can rewrite that equation and add all of my delta H's together. So I have P4O10 plus 6 PCl5 yields 10 Cl3PO. Now, how do I figure out this delta H? Well, I take all of the delta H's that I have here, this one, this one, this one, and this one, and I add them, watching the signs, because some are negative, some are positive, and I add them all together. So the overall enthalpy of this reaction, when I add negative 2857 plus 2967.3 plus 505.2 plus a negative 1225.6, I get an overall reaction of negative 610.10 kilojoules. So that is the overall reaction. So that's using Hess's law. Hess's law, we can take all of these smaller reactions, manipulate them so that we can come up with a final reaction. These are the steps that it possibly takes, because remember, it doesn't matter what the steps are, we're always going to get to that same delta H. This enthalpy change for this particular reaction will always be negative 610.10. So that's not going to change no matter how we get there. And so in this case, how we got there was manipulating all of those reactions to form that overall reaction. Hope that makes sense. There's another way that we can use Hess's law, and that's by using standard enthalpies of formation. And standard enthalpy of formation is actually written, you can see I have H sub F written there, but if I'm talking about a standard enthalpy, meaning the reaction was done at standard temperature and pressure, I would write delta H with that little degree sign that shows that's what we're using, is that standard enthalpy of formation. And that's basically just the energy needed to make 1 mole of compound from its simplest elements. The delta H's of formation were all found experimentally, and they're actually compiled into a table that's found in your appendix. in your textbook. And that's on page A19 in the back of the text, and you'll need those tables to solve these types of problems. Once you know the enthalpies of formation for all of the reactants and products in your reaction, you can determine the enthalpy of reaction, which is would be written delta H with that little degree mark and the R. So that gives us the enthalpy change of the reaction using the standard enthalpies of formation. So on the next slide, I want to show you the table at the back of the book, and I want to show you how to use that table. So what I did here is I copied one whole page. Now this is pages long in the back of your textbook. I just copied one page. There's actually 4 columns in that page, and you can see I kind of zoomed in on part of the page there. There's the substance and the state. So was it solid, liquid, or gas? Because remember, something like water is going to have a different delta H of formation if it is a solid or liquid or a gas. So you want to make sure that you know the states of the things that you're using. Now on this zoomed in portion, we are going to be making sure we use the delta H of formation. We're not doing delta G and we're not doing S yet. We're going to be doing those later. So right now you just want to focus on that second column, the delta H of formation. And notice it says kilojoules per mole. And we're going to talk about how we're going to convert that to just kilojoules as we go through some example problems. And I have 2 example problems to go through with you. So just make sure when you're using the appendix, you're using that delta H of formation, and you are making sure that you're looking at the proper state of the material that you're using in the reaction. Okay, real quick on this slide, I know we know the difference between endo and exo and the signs for delta H, but I want to focus on the breaking bonds and the forming bonds in this particular slide. And I'm just going to box those out so you can see. Energy is actually needed to break bonds, and so energy is going to be pulled into the reaction to break the bonds, and then when bonds reform, it's going to give off energy. So we can look at or compare the energy of bonds breaking and the energy of bonds forming. So if the energy, let me switch colors here, that's not a good color down here. Okay, so energy of breaking, if that is greater than the energy forming bonds, then the overall reaction will be endo, and our delta H would be positive. Okay, so that's what I'm kind of wanting to look at. Now the opposite's true. If I change that sign and I say that formation is greater than breaking, then it's going to release more heat when the bonds form than when they break. So then this reaction would be exo, and delta H would be negative. So we can kind of make some predictions based on what the sign of the enthalpy is, as far as was there more energy to form bonds or more energy to break bonds. So I just wanted to quickly mention that as we move on. Now real quick on this slide, this right here is the reaction that, the equation that we're going to be using to figure out the delta H, or the enthalpy change of the reaction. We're going to be using the standard states of heats of formation, and notice I have products minus reactants. So all of the products that are formed, we're going to add them together. If you have never seen this sign, it's a summation sign. So we're going to take the sum of all the heats of formation or enthalpies of formation of the products, subtract it from the sum of all of the heats of formation of the reactants or enthalpy change of the reactants, and that will give us our overall reaction. So this is just another way to use Hess's law. So let's dive right into some examples. Okay, here's the first exercise we're going to work on. It's page 249 in your book. You can see off to the right upper corner, there's a table in your textbook that gives you standard enthalpies of some of the compounds, the formation of the compounds. This is just a very condensed version of what's in the back of your book, and it's actually just put there so that you can look at the examples in your textbook and use that little table instead of having to go back and forth. Now, I will tell you, when you do your homework problems for these, you are going to have to go to the back of your book and look things up. They won't all be in table 6.2. So let's look at the first reaction. I have 2 products and 2 reactants. What I like to do with these is rate the delta H of formation for everything that's in the reaction and then go back and do the math. Okay, so if I look at the table, I can see that the delta H of formation for ammonia is negative 46. And I'm just going to write this quickly on this one just so you can see why it's kilojoules per mole. And then this 4 means that I need to multiply that negative 46 by 4 because I have a coefficient of 4 for the ammonia. What does that 4 mean? The 4 means, in a chemical reaction, 4 moles. So if this is 4 moles, then my moles in the numerator here cancel with my moles in the denominator there, and I'm left with kilojoules. And so our enthalpies of reaction are going to be in kilojoules, not kilojoules per mole, because all of the moles will cancel. For oxygen, if you look at the table, you're going to see that it's negative 800 and... Oh, I'm sorry, it's 0. I was looking at the wrong problem in my notes. This is actually 0, and 7 times 0 is going to be 0. Our elements are always 0, okay? If you look at the table, it's not listed in that table, but if you looked in the back of the book, in the appendix, it should be there, and it should say 0. On the product side, I have NO2, and I have 4 of them, so it's 4 times 34. And then for water, notice water is a liquid, and I have 6 moles of them, and it's negative 286. So when I do the math for all of this, remember I'm taking the sum of the products, subtracting sum of the reactants. So products are going to come first when I start manipulating these numbers. So delta H of reaction, I always put RXN. But your book uses R. Again, college, that's what I did, but your textbook's slightly different. 4 times 34 is going to give me 136, and we're at kilojoules. And we're going to subtract 6 times negative 286, which is 1716. And I'm going to bracket those like so, and then I'm subtracting, and then I'm going to put my reactants on this side. My reactants on this side, it's negative 184 minus 0, like so. And when I do the math here, I'm going to get an overall, and I think you can all do that, adding and subtracting in your calculator. You should get negative 1396 kilojoules for this particular reaction, and that's your delta H of reaction. On this side over here, you're going to have a negative here, and a negative here. You're going to end up adding the 184, and that's how I arrived at the negative 1396 kilojoules. Okay, so just watch your signs in these. That's probably the biggest concern I would have as far as these problems go, is because there's negatives and positives and you're subtracting, and so that's why if you bracket things and do things individually, it should make it a little bit easier. All right, let's take a look at one more example. Again, you can see here that I have table 6.2 off to the right upper corner. This is example 610 in your textbook. It's on page 251. And let's get started. Aluminum is an element. All elements are going to be 0, so aluminum doesn't count. Fe2O3, I have one of them, and the delta H of formation is negative 826. So those are my reactants. On the product side, iron is an element, so 0. 2 times 0 is 0. And aluminum oxide, I have one of them, and it's negative 1676. Okay, now, again, it's products minus reactants. So to solve for my delta H of reaction, I'm going to take the products, negative 1676, and I'm going to subtract negative 826. Again, units are kilojoules. I'm just not showing them there. And when I do the math there, I come up with a negative 850. And I'm going to put a little decimal there for sig fig reasons. And that's kilojoules. And that is it for Hess's law. Hopefully I gave you enough examples this time. Again, if there are any issues or concerns with anything as far as the examples or the homework, please ask. I am posting homework keys, videos that show how I solved all the problems, so you can take a look at those if you feel that you need to see any problems worked out. Okay. The next thing we're going to talk about is your assignment. Okay guys, here's your assignment. I want you to do numbers 60, 61, and 67. They will be either doing the first type of problem that we did where you're given a few reactions and you have to come up with the overall, or you could be using the summation that we just did in the end. These are on page 269. Please make sure you handwrite your assignments. That doesn't mean you have to do it on loose leaf and take a picture and do that. You can do it in Notability. Just make sure you're handwriting and not typing. And then if you want to put a photo in a PDF and submit it that way, that's great. Just make sure that either way that you send things that I'm able to read the document so that I can check to make sure that you're doing work correctly and give you feedback if I need to. This assignment's not due until Monday, April 6th in the Dropbox, and it's worth 5 homework points. I hope this was helpful. Again, any questions, email or put a new topic in the forum and I'll get back to you as quickly as I can. Have a great day, guys.